The next important set of concepts to understand as we're beginning our study of ecology, something called the biogeochemical cycles. Now, before you start thinking, oh my gosh, that sounds so complicated, how am I ever going to understand this? Well, it's really not that bad. Just think about it for a second. Look at this word biogeochemical. That's like 7 syllables. That's a lot of syllables. Well, what does bio mean? Bio just means life or living. What does geo refer to? Geology, study of the earth. Okay, so we got bio, life. We got geo, earth. We're talking about chemicals, atoms and molecules. And then this idea of cycles. So what are we talking about? We're talking about the cycling of chemicals between the geo and the bio, between the earth and living things. And since it's a cycle, it's got to go back again. That's all that a biogeochemical cycle is, the movement of atoms and molecules from the geo, earth, we can think of that as being non-living, to the bio, life, and back again. Very straightforward. Here we have a picture of one of my favorite spring wildflowers. This is Sanguinaria canadensis, or bloodroot. And I took this photograph at the North Chickamauga Creek Greenway here in Chattanooga in the Hickson area. And it's one of my favorite early spring wildflowers. Just beautiful. And it's participating right now, or right as I took that picture. Biogeochemical cycles are happening right here in that picture. And one of the neat things about biogeochemical cycles is you participate in them every single day, every single moment of you're doing it right now. While you're listening to this voice thread, you think, I'm just sitting here listening to this voice thread. No, 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 no. You are participating in biogeochemical cycles. At least I hope you are. If you're not, somebody better call an ambulance. One of the things that helps us to understand this idea of biogeochemical cycles and your place within it is to look at or think of the environment as consisting of 4 compartments. And I refer to these as the 4 spheres of interest. And the reason that I use the terminology spheres of interest is because all 4 of these compartments end in the word sphere. So we start with the lithosphere. Litho referring to stone, the stone sphere. What are we talking about? Well, we're talking about the Earth's crust. We're talking about all of the rocks and the sediments and the layers of sedimentary rock and limestone and granite. We're talking about oceanic crust. We're talking about continental crust. We're talking about all of that stuff that makes up the outer layer of the Earth and is concerned with geological process and composed of geological materials. So the lithosphere, it's rocks and dirt and stuff like that. The next sphere that we're interested in is called the hydrosphere. Now, hydro, what are we talking about there? Well, we're talking about water, aren't we? So the hydrosphere. The hydrosphere is basically all of the water that's on the Earth. Now, when I drew, or when I put this image of the hydrosphere on, see little drops of water in there, I put it in here in a very specific way. Notice that it overlaps the lithosphere, okay, just like that. Okay, and that implies a couple of things. First, is there water in the lithosphere? Absolutely. It's called groundwater. There's water in the soil. There's actually water in the rocks, and under the rocks there's water in the lithosphere. Okay? Then we can talk about this boundary right here, and we can ask the question, is there water on the lithosphere? Well, the answer to that, obviously, is yes. We call them lakes and streams and creeks and rivers and, well, the oceans.
That's water on the lithosphere. But notice that there's a lot of water above the lithosphere. Is there water above the lithosphere? Sure. We call that water vapor. And clouds, that's water above the lithosphere. So the hydrosphere consists of all the water on the planet. And some of that water is going to be in the lithosphere. A lot of that water is going to be on the lithosphere. And there's also a lot of water above the lithosphere. And they are interacting. Water can move from above to on top, like this. And water can move from on top to inside, like this. It rains on the land and falls into the lake or the river or the ocean, and it soaks through the materials in the bottom of the ocean or the bottom of the lake or the bottom of the river into the lithosphere. The next sphere that we're interested in is an interesting sphere that we call the atmosphere. Now, you've heard of the atmosphere. That's all of the air that surrounds the planet. The atmosphere is about air. Notice once again that I drew this atmosphere sphere in a very specific way. Notice that it is overlapping the lithosphere. Is there atmosphere in the lithosphere? Sure there is. There's air in the little spaces between soil particles. There's air down in caves. There's air down in cracks of rocks. Plenty of air in the lithosphere. Is there any lithosphere in the air? Sure. We call it dust and things like that. When a sandstorm comes by and blows the sand up into the air, blows dust into the air, that's lithosphere in the atmosphere. Notice that we also have the atmosphere overlapping the hydrosphere. Is there atmosphere in the hydrosphere? Sure there is. We call that dissolved oxygen or dissolved carbon dioxide. If you're a fish, you're really interested in things like dissolved oxygen, oxygen that has moved from the atmosphere into the hydrosphere, because if you're a fish, that's what you breathe. Okay? Is there hydrosphere in the atmosphere? Well, absolutely. It's what we call water vapor and clouds. Okay? So these things, they all interact with each other. Now, while we're here at the lithosphere, hydrosphere, and atmosphere, these three spheres of interest all have something in common. What is one of our vocabulary words, actually a couple of our vocabulary words that we could use to describe all three of these spheres? Which ones of our vocabulary words describe these? Well, hopefully you came up with non-living, okay, because all three of these are non-living, and you may have come up with abiotic, okay? Non-living and abiotic all describe the lithosphere, hydrosphere, and atmosphere. But remember, we're talking biogeochemical cycles. We're talking about an ecosystem, and all we've got here are three non-living abiotic things. Well, we've got one more sphere of interest that we got to add to this, and I'll bet you can figure out what it might be, or you can go to the next page of the voice thread and find out. Were you thinking the sphere that has life in it? Were you thinking about maybe the biosphere? Oh, we've seen that word before, biosphere. That's part of that hierarchy, biosphere, representing all the living things on the planet. Okay, the lithosphere, that's all the rocks and geologic materials. The hydrosphere is all the water. The atmosphere is all the air. And the biosphere is all the living things, all of the life. And notice once again how things are overlapping. So we've got the biosphere, it overlaps the lithosphere. Is there biosphere in the lithosphere? Sure, we call them plant roots or worms or naked mole rats. Is there lithosphere in the biosphere? Well, yeah, actually there is. Now, most people don't go around eating dirt, although there are plenty of little kids that eat plenty of dirt. But we kind of get it a little more indirectly. It's in the food that we eat, the different things that plants remove from the lithosphere and incorporate into their living bodies, that then we come along and we eat the plants, or we eat the animals that ate the plants, and then we get those atoms and molecules in us. So we do have lithosphere in us. You can go back to way back in the beginning in the Bible if you want, and we know that it's from the dust we were formed, and that's lithosphere in the biosphere, and to the dust we shall return, just going the other way. Notice also that we have the biosphere overlapping the hydrosphere. Okay, is there biosphere in the hydrosphere? Sure, it's called fish and other aquatic organisms. Is there hydrosphere in the biosphere? Well, have you ever had a drink of water? Have you ever had a drink of soda or a cup of coffee? Well, that's mostly water, and that's hydrosphere moving into the biosphere. Okay, and how about this one? Notice that the biosphere is overlapping the atmosphere. Well, is there biosphere in the atmosphere? Yeah, called birds, among other things. Is there atmosphere in the biosphere? Well, try this. Take a deep breath. That's atmosphere going into the biosphere. And then let it out. Now we're putting it back. And by the way, you just participated in a biogeochemical cycle. Okay, we got our 4 spheres of interest, and we've kind of already alluded to this next important idea that we're going to add to this, but we need to look at what happens to matter when it comes to these 4 spheres of interest. What happens is that matter cycles among these 4 spheres, and we could show it like this. We could show soil washing into a river. We can show material going into the air. We can show the air going into the owl. That's when you all just took a big deep breath just a second ago. And we can show the matter going back into the lithosphere after plants and animals die. So we can show the cycle like that. But what's really important to understand is that it's nice and easy to show it as a nice circular cycle like this among the 4 spheres of interest. But keep in mind, the matter can go either way, right? You can take a drink of water, so now it's going that way. You go to the bathroom, now it's going that way. Breathe in, breathe out. Okay? We got matter going in this direction. We got water. We got air going into the water here. We got air going into the land over here. We got this going that way, and it's coming over here like that, and this can go over here like that. Oh, it's getting to be a mess, isn't it? That's why it's kind of convenient to just show it as a nice circular arrow. But it's important to understand that the matter is moving among these 4 spheres. It's moving among these compartments. Matter cycles. Matter cycles. Matter cycles. First law of matter, law of conservation of matter, cannot be created or destroyed. We just got to reuse it and recycle it. We're reusing the atoms and molecules all the time. Matter cycles. But wait a minute. In order to make that matter move in all these different directions, matter doesn't want to do that all by itself. It needs a little help. So let's go way back to the very first module, or the second module rather. What makes the matter move? Well, hopefully you remembered that the thing that makes matter move in a direction it wouldn't normally go, like from the air into an owl, or from an owl into the river, or from the river into the ground, what makes that happen is something called energy. Energy makes matter move. But you'll remember energy had a couple of rules. We had the law of conservation of energy, first law of thermodynamics, can't be created or destroyed. Yeah, that's fine. But energy also had to follow the second law of thermodynamics, which basically said that anytime energy makes matter move, some of that energy is going to get converted to heat. The quality of the energy is going to go down. That means you can't use the energy that's left after it does something to do the same thing. It's not going to be able to. It doesn't have enough oomph because some of that energy got turned into heat. So as a result of that, energy does not cycle. Instead, energy flows through the system. Energy flows. It starts off as higher quality energy, and it's going to end up somewhere else as lower quality energy. Okay? So energy flows through the ecosystem. And this has to be, you really need to get a grasp of this. Matter cycles, but energy flows. Matter cycles, energy flows. The energy that is going to flow through these four spheres, and it's going to make the matter move, usually comes in the form of light energy, high quality sunlight, and when it leaves in a lower quality form, let's see if I can get the word light up here, when it leaves in the lower quality form, it's going to leave in the form of heat. Okay? And you can't use the heat to make the matter cycle among these four components. So it flows in oftentimes as light, and it's going to leave as heat. Matter cycles, energy flows. Matter cycles, energy flows.
This has to be your mantra. Matter cycles, energy flows. Matter cycles, energy flows. Matter cycles, energy flows. All the time.
Okay, well, let's take a look at this idea of energy for a second. For the vast majority of ecosystems and living things on the earth, the source of energy that makes the matter cycle and energy flow comes from the sun. Now, there are a few ecosystems out there that don't get their energy directly from, or indirectly, either directly or indirectly from the sun. At the mid-ocean ridges and at certain very deep places in the ocean where molten material from the mantle can come up through, you get different kinds of ecosystems that are referred to as hydrothermal vents. And there are some very, very special things happen, and there are organisms there that can actually use the Earth's internal heat and capture that energy and send it through those ecosystems. There are some of those, but chances are you're never going to actually directly encounter them, and the ecosystems that you're a part of and that you're an integral interacting with, the ecosystems that are part of your life, virtually every one of them is driven by energy from the sun. Now, how much energy are we talking about anyway? Well, if you recall back when you did your activity and you had to measure your electricity for a week, and you measured your electricity in a unit called a kilowatt hour. And you might recall that you might have used, in a week, you might have used a couple of 100 kilowatt hours of electricity. In a month, most people use somewhere around 1,000 kilowatt hours of electricity. Some people use more if they live in a bigger house and lots of people. Some people use less. Some people might only use 500 or 600 kilowatt hours of energy of electricity in a month. But
We're talking about the average household using about maybe 1,200 kilowatt hours of energy, electrical energy, in a month. Well, how much energy is striking the earth from the sun? Well, that comes out to be 174 trillion 423 billion kilowatt hours per hour of solar energy strikes the earth. 174 trillion 423 billion kilowatt hours every hour of energy hits the earth from the sun. And that makes your little 1,200 kilowatt hours a month of electricity energy that you use in your house seem like not much. People say, we need to be using solar energy. Man, there's a lot of it out there, isn't there?
All right. Well, what happens to this 174 trillion plus kilowatt hours per hour of light that strikes the Earth? And you might want to use your little magnifying glass if you want to magnify the different parts of this image, make it a little bit easier to read. But it's not so much important that you know each of these individual little things. Here we have the solar energy coming in, okay? And when it comes in, certain things are going to happen to it. One thing that might happen to it is that it's going to get reflected. It's going to bounce off of things. It bounces off the atmosphere. It bounces off the water. It bounces off the ice. It bounces off of shiny things. Okay? It bounces off. And that reflected light goes right back out into space without ever having contributed anything to the Earth's energy budget. It bounces right off. And that reflected light accounts for 30% of the light that strikes the Earth bounces off without ever having done a thing. Okay? So now what about the light that's left? Well, the light that's left gets absorbed. It gets absorbed by the air. It gets absorbed by, so here we have absorbed by the air, absorbed by clouds, absorbed by the land, and absorbed by the oceans. It gets absorbed. And when it gets absorbed, what happens is that light energy makes air molecules, cloud molecules, land molecules, and ocean molecules move faster, which is to say, it gets converted to heat. And that heat energy then gets transferred by a variety of mechanisms back out into space. It's going to leave. Okay? It's going to leave. And when you measure all of that heat energy leaving the Earth, that comes out to be about 70%. 70% of the energy that of the original solar energy gets absorbed, converted into heat, second law of thermodynamics, radiated back out into space. Okay? Remember over here, we had 30% of the energy was reflected. So 30% of the incoming solar energy is reflected, never does anything, just bounces off. Okay? What's left gets absorbed and re-radiated as heat, and that's 70%. And assuming that your math skills are what they should be for you to be even taking this class, you should realize that we got a little bit of a problem here. That adds up to, of course, 100%. Okay, 100%. And we haven't gotten anything into the ecosystems yet. What's going on here? Well, of course, all of these percentages, they're not exact measurements. There's a little bit of measurement error. It does turn out that there is a little bit of light left over, and that amount is 0.023%, 23 one-thousandths of 1%. And that 23 one-thousandths of 1% of light gets utilized in a process called photosynthesis. 23 thousandths of 1% of the light that comes in and makes it through the atmosphere and makes it to the surface of the earth and is not absorbed by the air or the clouds or the land or the water, what happens is it gets captured by plants and it gets used in a process called photosynthesis. Now here is what is so important about that. That 23 thousandths of 1% of the total incoming sun's energy that gets captured and used in this process called photosynthesis is the energy that drives almost every single living thing on the planet, including you. All of the energy in your body is part of this 23 thousandths of 1% that was captured by the plants and participated in the process of photosynthesis. Every living thing that you're ever likely to come in any kind of contact with or see on TV or whatever, you, look at you, that's you. You can move, that's you. Where did that energy come from? It came from that 23 thousandths of 1% of the light that got captured in photosynthesis. 174,423,000,000,000 kilowatt hours per hour must be one heck of a lot of energy. Well, now we're back to kind of where we actually started this voice thread, talking about bio, living, geo, earth, chemical, atoms and molecules, cycles. We're going to look at 4 specific cycles that you need to kind of understand, and it's important to keep in mind certain basic ideas behind biogeochemical cycles. The first is that each biogeochemical cycle has a source or a reservoir. There is some place in the non-living part of the environment where this particular element or molecule is going to be. Okay, and that's called the source. There's also a place in the living part of the ecosystem where the element is going to go, and that's called the sink or the destination. And of course we're talking about the movement of atoms or molecules, and in order to make atoms or molecules move, you got to have energy, and that represents the driving force. So all biogeochemical cycles, there's a source in the non-living part of the environment where that material is. There's a sink in the living part of the environment where the material is going to go, and there is a driving force to get it there. Of course, since it is a cycle, eventually material is going to go from the sinks back to the sources again, and keep this material being constantly recycled. You'll notice over here on the right hand side of our voice thread page, recognize those words? Yeah, you've seen those words before. These are our pairs of vocabulary words that we looked at way back in the beginning. And this is really nice because when we're talking about biogeochemical cycles, we're talking about things going from the non-living to the living. But since it's a cycle, it's going to have to go back. We're talking about things that are an abiotic part of the environment becoming incorporated into the biotic part of the environment. But because it's a cycle, biotic things are going to get converted back to abiotic things. And finally, a lot of this stuff moves, a lot of these atoms and molecules move. They start off in an inorganic form, and via biotic processes, living processes, they get converted to organic forms. However, once they're in organic forms, other living processes can work on them and convert them back to inorganic forms. So you can really begin to see some good relationships between the terminology that we looked at earlier and how these biogeochemical cycles work. So now, let's talk about some biogeochemical cycles. The first cycle that we're going to talk about is one that should be quite familiar to everybody. It's probably the simplest cycle to talk about, and I realize that this page looks very, very busy, but it's really not too bad if you just follow along carefully and look out the window every once in a while and think about how this relates to you. And it will make sense. Okay, the hydrologic cycle. Hydro, we've already seen hydro once in the hydrosphere, so hydro is back again. Hydrologic cycle, that's just the fancy science way of saying the water cycle. So we're talking about the water cycle here. And remember, each of these materials in our biogeochemical cycles has to have a reservoir. So where are you going to find the water? It's going to be in the oceans, in the rivers, in the lakes, in the streams. The reservoir of water or the source of water for the hydrologic cycle is the liquid water on the surface of the planet. You also have to have a driving force, and in the case of the hydrologic cycle, that's going to be direct solar energy. The sun shines on the water that's on the surface of the earth. Now, when that happens, when the sun shines on the water, a process takes place called evaporation. That's number 3 here. And the water evaporates into the air. As the water moves up higher in the atmosphere, interesting thing happens. The temperature goes down. And as the temperature goes down, if conditions are right, that water vapor can then form clouds. And that process, number 4 here, is called condensation. When the droplets of water or the ice crystals in the cloud get big enough and gravity can then pull them downward, gravity pulls it back down to Earth in a process called precipitation, rain, snow, sleet, and hail. Now, you might notice a little trend going on here. All of the processes so far in the water cycle end in TION. So we got evaporation, condensation, precipitation. Yeah, we're not done with that. When the water gets back down to the earth, it's got a couple of choices. One thing that can happen is that it can soak in to the ground and eventually work its way back to, via the rivers and lakes and streams, back to the ocean, back to the reservoir. And this is a process called infiltration and percolation. Infiltration is a big long word that means soaks in. Percolation is a big long word that means flows underground. Now, so far what we've got is a cycle. We've gone from the reservoir back to the reservoir, but so far we haven't gone through any living things. What we have at this point is called a geocycle, because we haven't got any bio involved. And it turns out there's another route the water can take that also does not involve the bio necessarily. Some of the water does not soak in to the ground, but instead it collects on the surface and it runs off into the reservoir again, into the rivers and eventually into the ocean. And that's a process called collection or runoff. Shun. Okay, well, just runoff. And once again, we've gotten the water from the reservoir back to the reservoir without ever having passed through a living thing. Okay, so what do we got to do next? We got to get the bio into the biogeochemical cycle. Okay, so we've seen how we can move the water from the reservoir through the atmosphere and the lithosphere and on top of the lithosphere and back to the reservoir without ever having gone through a living thing. Well, let's get the water to actually participate in a biogeochemical cycle now. So we have our evaporation that takes place, and the water evaporates and condenses, and then the condensation, the water gets heavy enough and we get precipitation, And then when the water gets back down to earth, it does infiltration and percolation, and now it's part of the groundwater. Well, as that water is moving through the ground, it's going to encounter plant roots. We could call this interception if we wanted to get another good TION word in there. So the water undergoes interception by plant roots, and the plants, in this case these pine trees, draw the water up into the plant. Now, in its journey through the plant, the water does a lot of really interesting and amazing things, and I highly recommend that you would take a general biology course or something, and you can find out all the cool stuff that happens to the water inside the plant. But eventually, as the water is doing what it does in the plant, and it's getting taken apart and put back together and all kinds of stuff, it's going to eventually come out of the plant through the leaves and back into the atmosphere. And this is a process, the movement of water from the soil through a plant and back to the air, called transpiration. Transpiration. And that water that comes through the plant and then leaves the plant through the leaves, I guess that's why they call them leaves, huh? Because stuff leaves through them. Well, not really, but that's pretty good anyway. That water is in the form of vapor, and it rises in the atmosphere, and it can condense, and we begin with condensation and precipitation and infiltration and percolation, and eventually that water can work its way back to the reservoir. And so now we have some bio in our biogeochemical cycle. Plants are an important part of the bio in the hydrologic biogeochemical cycle. All right, so what about our moose over here? We got to get the moose something to drink. Well, once again, the water is going to evaporate from the reservoir, rise in the atmosphere, cool, condense, condensation takes place, the water drops get heavy, precipitation takes place, and now we get water that is collecting and running off, collection and runoff in the form of lakes, rivers, and streams, and that's where the moose lives. So as the water is moving by the moose on its way back to the reservoir, the moose is going to intercept some of that water, and the moose is going to engage in a process called consumption. Consumption, just a lot of syllables that means moose is going to take a drink. All right, and that's how you get your water. You might have a bottle of water by you, or a bottle of soda, or a cup of coffee, or something else. Water, you take a drink. Consumption. Of course, now, water goes in the north end of the moose there, but this is a cycle. So that water's got to go somewhere. And where's it going to go? Well, it's going to come out the south end of the moose. And that's a process called excretion. And yeah, it's natural. It's what happens. Moose goes to the bathroom. And that water then can infiltrate, percolate, collect, run off. One way or another, it's going to end up back in the reservoir. It's probably a good thing that the process of evaporation sort of takes care of a lot of that stuff, and it's just pure water vapor that turns into clouds and precipitation and whatnot. We don't have to worry about any of these excretion things here. But this is also an important point. You know, when you're studying something like the hydrologic cycle, well, look outside. You see any clouds in the sky? Condensation. Is it raining today? Precipitation. Is the sun shining? Evaporation. Are you thirsty? Consumption. Do you have to go to the bathroom? Excretion. It's not, I've got to go to the bathroom, or it's not nature it's calling. Now you got a new thing to say. Got to go do my part for the hydrologic cycle. You're a part of all of these cycles, and that's one way that you can remember this stuff, is you can see how it relates directly to you. Now, the second biogeochemical cycle that we're going to look at is a little more complicated, but if we go through it slow, shouldn't be too hard. This is the carbon/oxygen cycle, although I'll probably just refer to it as the carbon cycle. But you can't really talk about carbon without kind of talking about oxygen at the same time. They both work together in this particular cycle. Now, the reservoir for the carbon cycle is the atmosphere, and the carbon is in the form primarily of CO2, carbon dioxide, in the atmosphere, and the oxygen in the form of O2 in the atmosphere. So that's the reservoir. The driving force is going to be direct solar energy. The actual sunlight itself is what drives the carbon-oxygen cycle. All right, let's take a look at what happens. The first thing we're going to look at is the carbon dioxide molecule. In the carbon and oxygen cycle, the carbon dioxide molecule gets taken up by plants. Okay, so the carbon dioxide goes in the plant like that. And immediately, while that carbon dioxide is being worked on, an oxygen molecule is going to be released. So the carbon dioxide goes into a plant, oxygen comes out. And this is a process called photosynthesis. Photosynthesis. Photo meaning light. Okay, so the sunlight, that's the photo in photosynthesis. We got sunlight coming in here. Synthesis is a word that means putting together. So we're using the energy in sunlight to put something together. And what we're putting together are carbon dioxide molecules and water. And one of the products of that, one of the things that happens as a result of that, is that we produce oxygen. Okay? So this is half of the carbon-oxygen cycle. Next, let's look at what happens in the second half of the cycle. Okay, so remember now, the carbon dioxide went in and oxygen came out in the first half of the carbon cycle, and this was a process called photosynthesis. What happens in the second part of the cycle? In the second part of the cycle, oxygen is going to go in. Notice that it goes into the plant, but it also is going to go into the animal. Okay? Oxygen goes into the plant and into the animal. And what's going to come out? Well, carbon dioxide comes out of the animal, and carbon dioxide also comes out of the plant. And this is a process. This is a process called respiration. Now, respiration, we're not talking about breathing here. We're talking about something that happens in the cells of the plants and the animals. It's a chemical reaction. Just like photosynthesis is a chemical reaction, respiration is a chemical reaction. Sometimes we refer to this as cellular respiration or aerobic, meaning with oxygen, cellular respiration. Photosynthesis, we put things together. In respiration, we take it apart. We use oxygen to take the molecules that were produced in photosynthesis and break them apart back into basically carbon dioxide and water. Now, we haven't shown the water in this. We don't need to. The important thing is that we get the carbon dioxide put back into the atmosphere where it came from. We get the oxygen put back where it came from. And so we have a complete cycle. The carbon cycle, the reservoir is the atmosphere, the driving force is sunlight, the process is photosynthesis to take the carbon from the abiotic to the biotic. It gets incorporated into organic compounds, and then respiration takes organic compounds apart using oxygen and puts the carbon dioxide back. That's really all there is to it. Well, almost. Let's look at what happens in this little relationship between photosynthesis and respiration. Now keep in mind that the plants do photosynthesis and the plants also do respiration. Okay, they do both. The animal, on the other hand, only does respiration. The plant's not, or the animal is not doing any photosynthesis. Plants are the only things that are going to do photosynthesis, or photosynthetic organisms, most of which are plants. We'll see a little more about that in another voice thread. Okay? But plants are doing both. Well, what would happen if plants did as much photosynthesis as they did respiration? If they took apart as much as they made? Well, if that were the case, if they were equal, then the plant couldn't grow. If it used as much as it creates, it makes it in photosynthesis and takes it apart in respiration, and if those are equal, well, it's not going to get any big. The plant's not going to get any bigger. What if the plant did more respiration than photosynthesis? Well, now it's using more than it's making. You know, if you eat 1,000 calories a day, but your body requires 2,500, what's going to happen? Well, you're going to lose weight. Okay, same thing with the plants. If the plants only make 1,000, but they use 2,500, they're not getting any bigger. In fact, they're getting smaller. And you know, we can go back and say about if it's equal. If they make 2,500 and they use 2,500, they're not going anywhere. But what do plants do as the rain waters the earth and the sun shines? Plants grow. Plants get bigger. How do they get bigger? They get bigger because plants do much, much more photosynthesis than they do respiration. They make more than they use. They make more than they use. That extra that they make in the process of photosynthesis, that extra carbon that they bring into the biotic part of the system through photosynthesis, goes into what we refer to as short-term storage for carbon. It's going to go right down here into number 5, short-term storage. We have some other names for short-term storage of carbon. One of those names is biomass, but there's another name for this that should be very, very near and dear to your heart. The other name for carbon in short-term storage, because plants do much more photosynthesis than respiration, is food. The food that the horse eats over there, the food that you eat. All of it started off right here. Food is carbon in short-term storage, also known as biomass. That's what allows the plants to grow. That's why it's so important that plants are out there doing photosynthesis, and the fact that they do much more photosynthesis than they do respiration, because that extra photosynthesis goes into carbon in short-term storage, creates biomass for the plant, and that's the food that we eat and all the other animals eat. Now, when we say short-term storage, we're talking about carbon that's going to be out of the atmosphere for a period of time, and it might be out of the atmosphere for a matter of hours, or it might be out of the atmosphere for days or weeks or maybe 6 months, or you know, this is going to make tree trunks and branches and stuff like that, and a tree might live to be, you know, several hundred years old, and there are some trees that are over 1,000 years old. And when those trees fall or die, they're going to break down, and that's a respiration process, and the carbon dioxide is going to be returned. But you know, you have a 200-foot tall redwood tree, and it's going to take that thing a while to break down. And so we're still talking about maybe 100 years or more. So short-term storage, yeah, we're talking hundreds, maybe 1,000 years or more. But relatively speaking, at least in geologic terms, that's just a very, very short term. Well, of course, if we have short-term storage, and as you can see on the voice thread page here, we also have long-term storage. We'll talk about that next. All right, the plants are growing, they're adding biomass, and that biomass that the plants are adding through the process of photosynthesis then goes on to feed animals. And animals, if they consume more food than they need in terms of their energy needs, then they will get bigger. And quite frankly, they put on biomass, okay? You're not gaining weight, you're adding biomass. That's just another word for it. All right? But what happens if this plant were to die and were to find itself in a situation that was short on oxygen? Say it falls into a swamp, it gets covered with sediments, and there's not very much oxygen. And if there's not very much oxygen, then there's not going to be very much respiration. And that means there's not going to be very much CO2 being released back to the atmosphere. In that situation, that carbon is going to remain in what was the biomass of the plant. It will probably get transformed over long periods of time. Now we're not talking about hundreds of years or thousands of years. Now we're talking about hundreds of thousands of years or millions of years or tens of millions of years. And that's carbon that's going to be put in long-term storage. Okay? Another fancy word for long-term storage is, we'd say that the carbon is sequestered. It's taken out of the system and it's kind of put away. This is like what happens in your, in your paycheck. When you get paid, okay, now your checking account is bigger than your debts, you hope, and as you go through the month, while you're using all that money that you made, it's like photosynthesis in spending money, that's like respiration. You put some of that money into your savings account, and you hope it's there in a year or 2 years or whatever. But if you've got a good job and you've got retirement benefits, some of that money is going into your IRA, okay? And that's like your long-term storage. You're putting that away, and you don't want to touch that. That's way back here. That's money that's being sequestered. Well, here we got carbon that's being sequestered. It's being taken out of the system for an extended period of time. And we have another name for carbon in this form, and it's something that I'm sure you've heard of called fossil fuels. This is coal and oil and natural gas. That's carbon in long-term storage. And if there weren't any human beings on the planet, there would be coal out there in the Appalachian Mountains and in many other places in the world. There would be oil under the north slope of Alaska and down in the Gulf of Mexico and in the Middle East and all these kinds of places. That would all be there. And if there weren't people around, how long would you expect it to stay there? Well, kind of pretty much expect it to stay there forever, because no other living thing uses that stuff. And it's just going to be there essentially forever. Okay? But humans are here. And what are we doing with the carbon that has been sequestered over hundreds of millions of years in the earth? We're taking it out of the earth and we are returning it back to the atmosphere in the form of carbon dioxide when we use coal in our power plants, and when we use coal for other purposes, when we use petroleum for a myriad of purposes, not just for automobile fuel, but for making fertilizers and things like that. We use an incredible amount of this material and we put it back in the air. And when you think about it, what's happening faster? The carbon going in to long-term storage, sequestering carbon, or the carbon coming out of long-term storage? Well, I think it's probably pretty obvious that we're taking it out a lot faster than we're putting it in.
And if you take money out of your savings account faster than you put it into your savings account, what's eventually going to happen? You're going to run out. And so when they say there's an end to the fossil fuels, fossil fuels are non-renewable resources. Once we use them, it's gone. Okay, that's it. But we also talk about things like climate change and global warming and whatnot. Well, the processes that would be taking the carbon out of the air, the carbon dioxide out of the air, that's plants, that's photosynthesis. Well, human beings are doing an awful lot to reduce that by deforestation, cutting trees down, things like that. It takes a long time to convert plants into coal and oil and gas. It takes, hundreds of thousands, millions, tens of millions of years. But it takes us almost no time at all to blow up the mountain, strip out the coal, burn it in a power plant. People don't have any notion of how quickly an electric power plant can burn coal. Here in the Chattanooga area, our closest coal-fired power plant that TVA runs is the Widows Creek Power Plant, and it's actually down near the Alabama line, a place called Bridgeport, Alabama. It's a moderate-sized TVA power plant, and they burn, on average, approximately 400 tons of coal an hour. 400 tons an hour is what they burn. How long do you think natural processes would take to form 400 tons of coal? I'll bet it takes more than an hour.
Now we're at the big one, the nitrogen cycle. Why do we care about nitrogen? Well, nitrogen is a pretty important element. It's a component of things like your DNA, and that's important to me. It's an important component of another type of molecule in your body that's extremely important called protein, and nothing in biology happens without proteins. It's all about proteins. And protein is not just meat, it's not just muscle. Proteins do an incredible number of different things in every living organism, from the smallest single-celled bacteria to you, to an elephant or a blue whale. Proteins make everything happen. Nitrogen is found in chlorophyll, and chlorophyll is where photosynthesis takes place, and I hope that after the discussion of the carbon cycle that you realize the incredible significance and importance of photosynthesis. And we want photosynthesis to go without a hitch, and that takes nitrogen. And nitrogen is found in a lot of other important places too. Nitrogen is very important, and it's important that we understand how the nitrogen cycle operates. Now, the nitrogen cycle is kind of complicated. There is a nitrogen cycle in your textbook, and it's kind of complicated. We're going to take it just a step at a time. Don't make it any harder than it is, and you'll get a general feel for how it works. We'll start with talking about the reservoir of nitrogen. Where is the nitrogen? Well, the reservoir of nitrogen is the atmosphere. There's nitrogen in the air, and in fact the air is about 78% nitrogen. Okay, a lot of nitrogen in the air. No shortage of nitrogen. 78% of the air you breathe is nitrogen. The problem with it is that the nitrogen in the air is in the form of what we would say N2. Nitrogen gas is N2. And these two nitrogen atoms are bound together with a triple bond. And triple bonds are notoriously hard to break. It requires a lot of oomph to break that triple bond. And it turns out there are three basic ways we can do it. One way to break that triple bond, we need a really huge input of intense energy. Can you think of anything that happens in the atmosphere that would represent an intense burst of super high energy? Well, maybe if you were thinking about something like lightning, like that, that'll do it. Lightning can break that triple bond. Lightning in a thunderstorm might be kind of dangerous for us, but it's really good for the ecosystem because it breaks those triple bonds. That's one way to do it. Another way to do it is something that human beings have devised. Now, I expect that hardly any of you have ever heard of a gentleman by the name of Fritz Haber. He's probably the most important person that nobody's ever heard of. But Fritz Haber was a German chemist way back in the late 1800s, early 1900s. And in the early 1900s, he discovered a process for taking nitrogen from the atmosphere and basically turning it into nitrogen that is available to plants in the form of fertilizers. And the Haber process is extremely important even today. And you can imagine, wow, we start putting fertilizers on our crops. You know, before Haber, you had to either get your fertilizer from natural sources, which wasn't always easy, or you just had to grow whatever the ground could grow. But with Fritz Haber, now all of a sudden we have the ability to add more nitrogen. It's an extremely important plant nutrient. All of a sudden our ability to grow food just increases dramatically. Yields go way up. Now we can support more people on the earth. It is just unbelievably important what the Haber process, that's H-A-B-E-R, Fritz Haber, what that did for human beings. And his process basically requires large inputs of energy in the form of fossil fuels to create very high temperature heat to break that triple bond. Now, there's also another little human kind of aside. There wasn't a lot of this necessarily in Fritz Haber's time in the late 1800s, early 1900s, but it was just getting started. And in essence, it's a similar kind of process to the Haber process, but it's something that most of us do on a daily basis. And we contribute to breaking nitrogen triple bonds. We get into our automobiles and we fasten our seatbelts, I hope, and we take the key and we put it in the ignition and we give it a turn and the engine starts. And what's going on inside that car's engine? An electric spark that's like lightning. We have high pressure as the pistons are compressing the gasoline. We have an explosion of air and gasoline, an intense burst of energy, and it breaks some triple bonds, and as a result, nitrogen compounds come out of the tailpipe. Unfortunately, those nitrogen compounds are a source of pollution. Okay, so we have lightning, that can do it. We have human processes, the Haber process or internal combustion engines that can do it. But there's another way to get the nitrogen and make the nitrogen available. And this way is the best way to do it of all. The best way to break this triple bond right here, outside of a good thunderstorm, is to make use of little tiny organisms that occur in the soil and in the water and everywhere called nitrogen fixing bacteria. And that's these little guys right here, nitrogen fixing bacteria. When we make abiotic inorganic nitrogen available to living things, that process of making the nitrogen available for living things to use is called fixation. Okay? So when we say nitrogen fixing, we mean making N2, atmospheric nitrogen, available to living things. Lightning does it. Automobiles and the Haber process does it. Certain bacteria can do it. Now, there are certain bacteria, certain nitrogen fixing bacteria, that live in the roots of plants that we call legumes. Legumes are plants that, they have pod-like fruits with bean-like seeds in them. Beans, peas, clover, kudzu, redbud trees, black locust trees,
These are examples of legumes. Any kind of bean or pea or clover or something like that is an example of a legume. And legumes do something special. On the roots of the legumes, they form these little bumps of tissue from the roots, and these are called nodules. And inside of these nodules, over here we're taking a peek inside a nodule right here, there are nitrogen-fixing bacteria, but they're not just any nitrogen-fixing bacteria. They're a special group of nitrogen-fixing bacteria called rhizobium. Rhizobium lives in the nodules that form on the roots of legumes. Basically, now, the driving force of the nitrogen cycle is going to be indirect solar energy. The sun shines on the plant does photosynthesis, makes food. The rhizobium can then use that food, and it's living in the nodules, so it's getting room and board. And it has the biochemical machinery to be able to run certain chemical reactions that allow it to fix nitrogen. And that fixed nitrogen then is available directly to the legume plant. And if you think about it, beans, peas, peanuts, soybeans, what nutrient are they really high in? Well, they're really high in protein. Why are they so full of protein? Because they've got ready access to nitrogen, just a direct shot from these little rhizobium bacteria that live in the little apartments, the little nodules that form on their roots. So the rhizobium bacteria, they get room and board, and in return, they pay their rent through fixing nitrogen. Pretty neat setup. Now, the nitrogen that the rhizobium fixes goes into the legume. The legume then uses that nitrogen to make chlorophyll, protein, all kinds of other things. That nitrogen then, we said, has been assimilated. Living things, the plants assimilate the nitrogen. All right, then here comes the bunny rabbit. Hop, hop, hop. And the bunny rabbit, hop, 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 munch, starts eating the legume. Okay? And they eat the legume. And the nitrogen that was in the legume now is going to end up in the bunny rabbit. Okay? Nothing wrong with that. Now the nitrogen's in the bunny rabbit, and the bunny rabbit assimilates the nitrogen and uses the nitrogen. Okay? And the bunny rabbit's going to turn it into protein, and it's going to turn it into DNA and all kinds of other good stuff. So we have assimilation. It's coming out of the atmosphere through nitrogen-fixing bacteria into legumes, into bunny rabbits. Okay, the nitrogen going into the north end of the bunny rabbit. But as we've already seen with the hydrologic cycle, if something goes in the north end of the animal, well, something usually comes out the south end of the animal. And in this case, we're talking about waste products or when the animal dies. An animal's waste still has nitrogen in it. Bunny poop has nitrogen in it. Bunny pee has nitrogen in it. And bunnies themselves have nitrogen in them, just like you and I do. And when the bunny dies, when the bunny goes to the bathroom, those nitrogen-containing materials are now out in the environment. And we got to do something with them. Well, here is where we enlist the aid of more of our friends, the bacteria. Bacteria are so important. Bacteria don't just make you sick. Bacteria do many, many, many important ecological services, ecological functions. And one of the functions they do is they turn that nitrogen that's in the proteins and the other compounds that were in the bunny rabbit, they turn it into ammonia. And that process is called ammonification. If you've ever been associated with a little baby or know somebody who's got a little baby, you know they tend to go to the bathroom in their diapers and you have to change their diapers. And after you got 3 or 4 diapers in the diaper pail, you open the lid on the diaper pail and, oh man, it stinks. And one of one of the odors that just really, really does you in is ammonia. And that's because there's bacteria in there turning those nitrogen compounds into ammonia. Now, ammonia, that's not great stuff. We got to do something else to it. We have bacteria that make the ammonia, but we can't leave it there. We got to go to another step before it's something that's going to be useful to us. And that next step, which also happens to involve more bacteria. We got bacteria that do ammonification, and then we got bacteria that take that ammonia, and they're going to turn it into nitrogen that's going to be useful to us. And that process is called nitrification. And in nitrification, we're going to turn that nitrogen into compounds that any plant can use. So now your grass is using it, and oak trees are using it, and every kind of plant can use the nitrogen that's made available by nitrification. So, the nitrogen-fixing bacteria make it available to legumes. Legumes get eaten by animals. Animals go to the bathroom, animals die, legumes die. Bacteria ammonify the nitrogen compounds in the wastes or the dead plants and animals. The ammonia is not very good for us, so we got other bacteria that take the ammonia and they do a process called nitrification, which makes the nitrogen available to other plants. And then other plants assimilate the nitrogen, and animals come along and eat those plants, and they assimilate the nitrogen, and they die or go to the bathroom. We come along and we eat those animals and we eat those plants. We go to the bathroom. We die eventually. Those nitrogen compounds are there. They're coming out. Bacteria are going to turn them into ammonia. Other bacteria are going to nitrify them, and they're going to get taken up by plants again. Of course, if you think about that for a second, we got nitrogen coming in from the atmosphere, and then we got nitrogen kind of cycling here in the biosphere. It's just kind of going around and around and around and around and around in the biosphere. But if that's the case, what's eventually going to happen up here in the atmosphere? Okay, have we completed the cycle yet? Well, no, we haven't. The cycle is not going to be complete until we get the nitrogen back up here in the atmosphere. We're taking it out of the atmosphere, putting it in the biosphere, using it for a lot of important stuff, but eventually it's got to go back or it's not going to be a cycle. And the way we get it back, well, let's go back over and talk about ammonification and nitrification. Remember that after the nitrogen's been assimilated, certain bacteria do ammonification, turn it into ammonia. Other bacteria do nitrification, turn it into usable nitrogen. Well, there's even more kinds of bacteria out there who can take those nitrogen compounds after nitrification, and they can put it back in the air. And if nitrification is making it available, what do we call making it unavailable? Making it unavailable is called denitrification. We do a process called denitrification, and that puts the nitrogen back in the atmosphere. That completes the cycle. Whew, that's a lot, isn't it? All right, there's a lot to the nitrogen cycle, and once again, the nitrogen cycle was working just fine, and then people came along. And when people started messing with the nitrogen cycle, we start to cause some problems, a little bit of that oops effect that we talked about in a previous voice thread. What we do is we remove a lot of nitrogen in the form of nitrogen fertilizers. Our good buddy Fritz Haber and the Haber process to create nitrogen compounds. And we spread those nitrogen fertilizers on our agricultural fields, many, many, many millions of tons every year spread out on the fields. And of course the plants just love it. And the plants are just growing. Man, this is great. But the problem is, not all of that nitrogen that we put on the farmers' fields stays in the farmers' fields. it rains. Remember, rain, infiltration, percolation. Some of it gets carried down to the groundwater. You may have heard of nitrates in the groundwater, not too good. Some of it gets caught up in the collection and the runoff, and it washes into rivers and lakes. Well, you know, there's plants in rivers and lakes, and they like that nitrogen too, and they start growing like crazy. But the problem with a river and a lake is they have a pretty limited amount of oxygen. And so even though during the day the plants get all this nitrogen fertilizer, they're going, yeah, baby, we're growing like mad. What happens at night? Well, they're not doing photosynthesis anymore. They're not making oxygen anymore, but they're still doing respiration. And what happens is when a lake gets too much vegetation, and it's usually algae, we say we have an algal bloom. It seems like the lake just all of a sudden, or the pond is just all of a sudden full of algae. And at night, that algae sucks all the oxygen out of the water, and it kills the fish. And then the algae itself starts to die, and then stuff starts to decompose, and it's really, really disgusting.
The last biogeochemical cycle that we're going to look at, oh, it's the last one, what a relief, is the phosphorus cycle. The phosphorus cycle. Now, phosphorus is another important element that living things need for a variety of reasons. Phosphorus is an important component of an interesting little molecule called ATP. ATP. The P stands for phosphorus, the T stands for tri. So there's 3 phosphorus atoms in each ATP molecule, and they're very important because they help to move energy around inside of your cells. It's very important at the cellular level for energy and metabolism and making you be able to do the things you're doing. Phosphorus is also important in the actual structure of a DNA molecule. It gives it its form, and form follows function, especially with DNA. Phosphorus is very important in your DNA. And it pops up in a lot of other important places as well. So phosphorus cycle, it's really important, and it's what we're going to look at right now. This phosphorus cycle, is a little different than the cycles we looked at before. In the hydrologic cycle, the reservoir was the water, was oceans and things like that. In the carbon cycle and nitrogen cycle, the reservoir was the atmosphere. Now, the reservoir for our phosphorus cycle is actually rocks. It's phosphorus-bearing rocks, or what we call phosphate rocks. Things like limestone. Limestone is a really important rock that can have phosphorus in it. Other types of rock can have phosphorus in it as well. Some rocks have high concentrations of phosphorus, other rocks not so much. So the reservoir is rocks. Now, how do we get the phosphorus out of the rocks? Well, it happens because the rocks get exposed to the air and the sun shines on them and they heat up and they cool down and they get rained on and they get snowed on and water freezes and water thaws. And this is a process called weathering. And in the Earth Sciences module of the course, we talk about weathering in some detail. And the weathering, the breaking of the rocks down into sediments, releases the phosphorus, and the phosphorus gets released into the soil. And so this driving force, it's really indirect solar energy. But it's indirect solar energy working in various geological processes. Once the phosphorus is in the soil, woohoo, the plants love it. It is going to get in those plants, and they are going to use it for all kinds of things. And once it gets in the plants, it's now available to the animals, and the animals are going to use it. Woohoo! It's good for all kinds of things. And then the animals go to the bathroom, or the animals die, or the plants die, and where does the phosphorus end up? Back in the soil. And when it gets back in the soil, who's there waiting for it? Woohoo! The plants, and the plants take it up. and they turn it into good things. And once it's in the plants, the animals get a hold of it. Woohoo, that's pretty good. And the animals die, or the animals go to the bathroom, and whoop, gets back in the soil. I think you get the idea. The phosphorus is just going to spin around between the living things and back in the soil and back in the plants and back in the animals and back in the soil for a long time. The thing about phosphorus, though, oh, and by the way, that was our uptake and recycling. You may have figured that out. The thing about phosphorus is that it's very, very easy to dissolve in water. You remember back in the hydrologic cycle, we had the rain is falling and it's infiltrating and percolating and moving through the soil. It's carrying phosphorus with it. It's collecting and running off the surface. It's carrying sediment. It's carrying phosphorus with it. Okay, we have runoff and sediment, and what that does is carry the phosphorus into rivers, lakes, streams, and eventually the ocean. But that's not necessarily a bad thing, because ocean creatures, water creatures, they need phosphorus too. And so that's how they get theirs. It's what runs off of the land. And so they're happy, and the phosphorus gets taken up and recycled here within the aquatic system. But eventually, that phosphorus is going to settle out here on the bottom, and over time, it's going to get covered with sediments, and given enough time and given enough coverage, that phosphorus is going to be incorporated back into the rocks where it originally came from. And now we say the phosphorus is back to the reservoir, or it's in long-term storage, because those rocks that are at the bottom of the ocean, and they're going to be there a long time before they eventually make it back up here where weathering and release can work on them again. Now, people, yeah, we've kind of gunked up the phosphorus cycle a little bit too. Phosphorus will accumulate in certain parts of animals. In insects, it accumulates in their exoskeleton, and there's really interesting creatures out there that just love to feast on insects. We call them bats. Okay, so I'll draw a little vampire bat. No, not a vampire bat. A little bat right there. Oop, he needs little pointy ears. There we go. Some bats have really big ears. They call them big-eared bats. I wonder why. Anyway, bats fly around gobbling up mosquitoes, and during the day they go back to their cave and they roost, and they're back in their cave and they're digesting all these mosquitoes that they ate and all these bugs that they ate. And the next evening it's time to go out and catch some more, but before they take off, you know, I mean, the first thing, getting up in the morning, I mean, you know, what's the first thing most of us do when we get up in the morning? Well, I'll give you a hint. It's not brushing their teeth. It's the other thing they do in that room, and they take off and go catch some more bugs. Well, that bat poop begins to accumulate on the floor of the cave, and that bat poop is really high in phosphorus. And in fact, it is such an important and valuable natural resource, we give it a name, because if we called it bat poop, nobody would buy it. But it has another name. It's called guano. Guano, that is high phosphorus bat poop. And we actually go to caves and mine the guano for the phosphorus to use in fertilizers. Now, it's not just bats that are doing this. Remember all that phosphorus that's washing into the sea? Okay? Well, seafood is pretty high in phosphorus, and there's a lot of birds that love to just feast on seafood. So these seabirds are out there all day, and they're filling their tummies up with all these wonderful, yummy fish and stuff. And then in the evening, they, flap, and they get up on the cliffs where they're going to roost for the night, and they sit there all night and digest. And the next morning, before they take off to go catch another belly full of fish, they have to take care of certain natural functions, and I'm not talking about brushing their teeth. And that material, the seabird poop, accumulates at the bottom of the cliffs, and that poop is high in phosphorus, and it has a name. It's called guano. And human beings go and we dig that stuff up and we sell it as fertilizer.
So guano, phosphate, high phosphate manure, basically poop, from bats or seabirds. Now the thing is, we put that phosphorus on our fields. More phosphorus then is on the fields than the plants can take up. What happens to the excess? It washes into the streams and rivers, and the plants there go, yeehaw, lots of phosphorus, and they start growing like crazy. And is this beginning to sound familiar? Just like in the nitrogen cycle, the plants in the waterways grow way too fast, they get way too abundant, and the next thing you know, they suck all the oxygen out of the water at night and kills all the fish, and it's a big, nasty, disgusting mess. We need to be kind of careful how we utilize phosphorus.